All right, so let's look at an example of calculating bending stress. So as we went over here last time, when you load a beam, it'll bend. You have a neutral axis where there's no deformation. On one side of the neutral axis will be the compressive side of the beam, and the other side will be the tensile side of the beam. The further you are from the neutral axis, the more pronounced the bending. Okay. So what we ended up doing here was looking at that relationship and using the fact that there was a linear relationship between the distance from the neutral axis and the stress. And then we looked at the moment in the beam and equated that to the integral, which means to add up the stress, normal stress, times y, which is a moment arm from the neutral axis to wherever that stress occurs, times the area over which the stress acts. So the normal stress times the area over which it acts is a force. You can then come up with the y distance from the neutral axis to that force, which is a moment arm, and then add up every possible dA in this beam times its stress, which will get you a force. Add in the moment arm, you get a moment there. Okay. Now that's an integral, so it's sigma x y dA. You can put a term of y over y into that. And what that allows you to do is to pull out the constant sigma x over y, and that leaves the integral of y squared dA, which is I. So that gets us our basic equation here to find or to equate the moment and the normal stress in the beam together. We end up down here where we rearrange the equation and solve it for what we'd want to know, which would be the maximum normal stress in the beam, which is the maximum tension or compression. It's the moment off the moment diagram times the distance from the neutral axis to the extreme edge of the beam, which we call C, divided by the moment of inertia of the beam cross-section. Okay, so that's the basic beam design equation for normal stress right there. So we want to be able to apply this. All right, I showed you a picture here. You know, we've got a neutral axis in this beam somewhere around there. We're pushing down on it with two load points to get it into a smooth curve, and the failure is starting at the extreme edge of the beam. That's where that failure started, because that's where the tensile stress was maximum. So that distance from the neutral axis down to the edge of the beam is called C. That's the maximum possible Y. All right. So to find the normal stress, you take the moment off the moment diagram, multiply it by that maximum distance C, and divide it by I for the beam. All right, so let's have a look at page 840. We've got this L-shaped beam with the load applied, 2,000 pounds there, 7 feet over from A, which is 3 feet from C, which is where the supports are. So there's A and there's C. So I've got the cross-section of the beam showed over here on the lower left. I've got a long just line diagram of the beam showing that it's 10 feet long and has 2 supports. And then I've got an isometric, or actually a oblique 3D picture of it with the load on it. It's an L-shaped beam. So why don't you draw up the shear and moment diagrams there. You could give that a run, pause, and then we'll get to them. And then start the recording up after you've drawn them up. All right, so there we go with the shear and moment diagrams. We'd have a block-shaped shear diagram. We'd find the area under the blocks and use that to generate the moment diagram. So we go from 0 up to 600 for the reaction. Nothing changes till we hit 2,000. That drops us down to negative 1,400. We stay at that load until the reaction pushes us back up to 0. Okay, we got 7 feet, 600-pound height. So multiply those together for the area. It's 4,200. And then the area on the back side is negative 1,400 times 3. It's negative 4,200. All right, so that takes us on our moment diagram from 0 up to 4,200, back down to 0. So that gets us our maximum moment in the beam. It's 4,200 pound-feet. Okay, now our beam dimensions on the cross section are measured in inches, so I want to convert that into pound inches so it'll match. So I multiply it by 12 inches per foot and get 50,400 pound inches for the maximum moment. All right, so that gets me the first thing I need on the equation, which is m. Okay, now the next thing I want is c. To find that, I find the centroid of the beam. So I've got the two pieces here that I've marked A and B. I'll go ahead and find the areas of each of the pieces. For A, it's 2 by 10, it's 20. For B, it's 2 by 2, which is 4. Then I find the centroidal distances from my reference axis at the bottom of the beam to the centroids there. So for A, it's half of the 10, it's 5. And for B, it's half of the 2, it's 1. I'll put that information in the table. So 20 for the area of A, the y-bar distance of 5, 20 times 5 gets you 100. For B, the area is 4, the offset distance is 1, 4 times 1 gets you 4. I can find the total area. It's 24. I can find the total AY bar. Add that up, it's 104. Divide 104 into 24 and I get the y bar distance. It's 4.33 inches from the bottom. What that means is from the neutral axis to the bottom is 4.33 inches. And from the neutral axis to the top is 10 minus that, which is 5.67 inches. So those are my C values for the top and bottom. Okay. So now I got C. I need I, which is the moment of inertia about the neutral axis. So I start with this information. I'm going to have to use the transfer axis theorem to find this. So I start with part A. Its moment of inertia about its own centroid is bh cubed over 12. So 2 times 10 cubed over 12 is 166.7. Its area is 20. The distance from the neutral axis to its centroid is the difference between 5 and 4.33. It's 0.67. So I take the area times 0.67 squared. I get 8.9. That's my AD squared piece. And I add that to my IX, my bh cubed over 12, and I get the total moment of inertia of part A about the neutral axis. I can do the same thing for B. Find bh cubed over 12, it's 1.3. The area is 4. The distance from the neutral axis to the centroid of B is 1, which is the centroid of B, minus 4.33, which is where the neutral axis is. So that's a negative 3.33. There's a decimal in there. So I take the area times that negative 3.33 squared. The negative squares out, so it really doesn't matter that much. That'll just square out, and 4 times 3.33 squared is 44.4. I can add that to 1.3 and get the total moment of inertia for that part B. It's 45.7. Add it to the 175.6, and I get 221.3 inches to the 4. That's the total moment of inertia of the L-shaped beam about the neutral axis. Okay, now I got M, I got C, and I got I. So I can calculate up the maximum compressive stress, which would be the moment, times the C to the top of the beam, because that's where the compression is. The beam's bowing downward as it's loaded, so that compression will be on the top. So the beam bows into a shape like that because it has simple supports and it's loaded. And actually, it'll be a little bit more tilted towards this side where it's loaded, so that may not be perfectly accurate there. Might be hard for me to draw here on the fly, but I think it's maybe something more like that. I don't know. Whoops, well, that's not too good either, but you get the idea. So we've got that beam bending down. So the meaning of that is the compression's on the top and the tension's on the bottom. So C to the top is for compression, C to the bottom is for tension. So sigma C max is the sigma at the top. M max is 50,400. C max is 5.67. And I is 221.3. Work that out, and the maximum compressive stress in the beam is 1,291 pounds per inch squared. We can do a similar calculation here for the tensile stress. It's the same moment and the same I. What differs is the C, because now we're using the C to the bottom of the beam where the tension is. Use the maximum distance there from the neutral axis to the bottom of the beam. It's 4.33. And the tensile stress there, for the maximum tensile stress in the beam, is 986. So in most structural engineering, we'd use the same beam for the entire length. These would be our design values. Here's some typical stresses for Douglas-Fir. 1,100 pounds per square inch for compression, 1,300 pounds per square inch for tension. So we could look and see if we could make this thing out of Douglas-Fir. Okay, the tension looks like it's okay because the 986 is less than the 1,300. But the compression doesn't look like it's going to work because we've got too much stress in the beam. It's far above the allowable stresses. Okay. So there's just an example of a bending stress problem that we could work through there.